Hello everybody and welcome to Designing for Reliability in Production. Before we start, I would like to introduce myself. My name is Ayelet Sachto. I'm a strategic cloud engineer in Google Cloud UK, and I'm also co-leading PSO SRE practice in EMEA. I can put a pretty slide with all the top logos of companies that I work with to talk about startups that were purchased. But what you really need to know about me for the scope of this session is that I'm living and breathing production in large scale for almost 2 decades now, which provides me with the opportunity to design and implement a variety of architectures with different constraints. As you could guess from the name of the session, today's focus will be reliability, why it's important, and I'll introduce a few best practices for designing and running reliable production systems. At the end, I will also share with you how we can leverage SRE and share with you some resources to get started. Why we are focusing on reliability, why it's important that our service will be reliable. Put yourself in the user's shoes for a second. Let's say you are using an application with great features, but you can't trust it to work. Will you continue using it? Would you care if an application has an amazing UI and features if it just doesn't work? People sometimes replace reliability with availability. But reliability is more than just service availability, especially when we're talking about distributed complex systems. The definition of reliability is more complex if the service is down and if we are getting a response. Reliability is the ability to provide a consistent level of service at scale, which can translate differently in different services and include different aspects like availability, latency, and accuracy. Think about it. Does reliability mean the same for Netflix user and Google search user? Depends on your service, your user's expectations will be different, and reliability can mean different things. As a rule of thumb, a system is more reliable if it has fewer, shorter, or smaller outages. You probably heard of a 3.9 or 4.9 service, but it all comes down to the amount of downtime that our users are willing to tolerate. Here are a few answers that our customers gave about reliability and what it means to them. You can see that it all comes down to the customer, the user trust and satisfaction. We want to take a customer-centric approach because unhappy customers will leave. So if reliability is defined by our users, to understand what's the level of reliability we need to provide, we need to understand the user's expectations and measure them as closely as possible to the user expectations and experience. And later I'll expand about SLOs in that regard. So, how do we achieve our desired level of reliability? We need to design and run reliable system that meets our user expectation, which fundamentally mean to reduce the 4 X's in this equation. We need to reduce the time to detect, reduce the time to mitigate. We need to reduce the number of incidents that we had, which means to increase the time between failures. And we want to reduce the impact, the blast radius. So, for example, how many users are affected. Next, I will discuss a few strategies for reducing each one of those and to improve our reliability in our design. Before we jump to reliability best practices, I want to call out a few anti-patterns as well. And remember that we want to be able to make decisions based on data, and we also want to have resilient applications. So a few anti-patterns for that matter will be not to have monitors. If we don't have data, we are blind, we don't know where we stand, and we don't know where we're going. Doing global changes as normal is also an anti-pattern. For example, if we don't have gradual changes, or we are not using Canary or progressive deployments. We can be as reliable as our critical dependencies. So if we don't have any mitigation or degradation strategies, it's also an anti-pattern. It's better to degrade a service than not having a service at all. And we'll touch on it shortly. Lack of redundancies or positive feedback loop are also anti-patterns because they can overload the system and can actually cause cascading issues. Another anti-pattern is crashing when overloaded. And we'll talk shortly on a few things that we can address. And in the next section, we'll look on how we should address those anti-patterns and what are the best practices to do instead. To address those anti-patterns, I want to touch on three main topics. The first one is prepare for failures. In that topic, we'll touch on decoupling responsibility, avoiding global changes, having rollout strategies, avoid single point of failures, reduce critical dependencies, and also having degradation as a strategy, like throttling or load shedding. In the second topic, we'll focus on designing for reliability. Defense in depth, so ensuring that we have fallbacks, scaling horizontally, having microservices, geographically horizontal scale, and more. And of course, the principle of N+2. The third topic is data handling, or more specifically, avoiding keeping state and using caching and sharding for frequent access data. So let's zoom on each one of those. One of the fundamental architectural ways in which we can improve our resilience and our reliability is to build systems spanning across zones and regions. Designing systems that span these zones and regions or choosing products that do so automatically allow us to minimize the impact and provide some level of service. Using SLAs as reliability floors, we can assure reasonable expectation of reliability for our applications architectures using this construct. Extending to multi-zonal or regional will provide us a higher resilience and will lead us to general expectations of 4 nines. Extending this to a multi-region approach provides us a general expectation of 5 nines. Disclaimer, to reach 5 nines, multi-region is not sufficient, but is necessary. So I mentioned that failure is not a question of if, but a question of when. So we want to design our system to be resilient. So it is important to understand how do we deal with failures and to what type of failures we are resilient to. Can we tolerate unexpected single instant failure or a single instant reboot? Our system will deal with zonal or regional failures. So a good approach to mitigate the first examples of an instant failure or reboot will be to use persistent disks and startup scripts to quickly reconfigure software. And of course, we want to back up our data. To mitigate zonal or regional failures, we will want to have resources, diversity across region and zones, and of course, implement load balancing in front of them. In that regard, we will also want to replicate our data and have persistent disk across multiple zones. Other things that we will want to consider in regard to preparing for failures will be both in software design and processes, how to prevent and how to mitigate. Decouple responsibility, for example, avoiding monolith servers, designing microservice, reduce the blast radius when things do fail. As I mentioned before, we also want to avoid global changes. We want to use Canary changes and pause, see the impact when we're doing global rollout. That will allow us to mitigate the number of users affected by it. Spreading the risk and avoiding single point of failures is also a recommended practice. We don't want to depend on one backend. Lastly, we want to deaggregate gracefully. If you can't serve all your users with all the features, can you serve them with minimal features? Can you throttle user traffic and drop expensive requests? Better to be able to deaggregate and keep serving as long as possible. When we think about designing for reliability, we want to ensure that we have fallbacks, that we have defense in depth. If we rely on a system for configuration or other runtime information, we want to ensure that we have a fallback like a cache version that will continue to work when the dependencies become unavailable. Another good practice is to scale horizontally across different geographies, different data centers. It's also important to remember to have load balancer solutions in front of them and to avoid, as much as possible, special hardware. N+2 means you have N capacity to serve the request at peak. And then you have +2 instances to allow one instance of the complete system to be unavailable due to unexpected failure, and another to be unavailable due to planned upgrade. Be mindful that important and critical services might require more than just +2, which can increase the cost, but as a lot of things in architecture, it will be an issue of trade-off and priorities. Another critical aspect is dealing with data. We need to store, retrieve, and act on data. Data implies state, but the fact that we need to store the data doesn't mean it needs to be stored on the server itself. When we refer to stateless service, we mean that the server is not needed in order to keep the server information or session details. It's important to note also that some data is accessed more frequently than others. And for performance optimization, we might want to use sharding and caching. With caching, we are referring to partitioning your data on something in the request, for example, user ID, into N buckets. And with caching, I'm referring to moving the data access to faster I/O to handle more frequent data access, for example, RAM. We want to do it in order to reduce the overload on our servers and eliminate any possible bottlenecks due to I/O. We also want to think about consistency, a global view of our data, and performance. We want to prevent duplication of work, find closest data sources possible. So regardless of the amount of data involved, it all comes down to global consensus. One thing to remember is that we can be as reliable as our critical dependencies. And by critical, it means hard dependencies that we cannot mitigate. In that perspective, it's important to choose the right building blocks for us in our architecture and our design. When choosing the right building blocks, we will want to choose a GCP product that suits the level of reliability we actually need. Be mindful also of GCP building block scope, as I mentioned, zonal, regional, and global, and that those correlate with our application targets. When talking about design and architecture, there is no one-size-suits-it-all. We need to let our requirements guide us. Let's look at an example of a customer-facing web service design. And I'm specifically saying an example because this is what worked in our case. But designs will be very different depends on the scope, criticality, and traffic, to name a few. For our specific use case, we needed a backend that can scale rapidly, that can support millions of requests in a second globally, and that can support 25x increase in web traffic with an unexpected pattern. From a data perspective, we needed globally distributed data store. So for that, we chose to use PubSub to handle the 25x growth for requests between internal services, Spanner, the only enterprise-grade, globally distributed, and strongly consistent database service, as we needed the benefit of a rational database structure that can scale horizontally. We also chose GKE for horizontal scale, both for the front-end and back-end pods, as it can accommodate for the 25x increase in web traffic, with a combination of GCLB for load balancing. As we needed global solution and redundancy, we used multi-region GKE clusters, GCLB as mentioned, and 3 availability zones. To ensure reliability, it's also important that we'll have a robust CICD pipeline. For that, we use the CICD stack for source control management, continuous integration and delivery, artifact management, and software supply chains. We also used Terraform to automate the deployment and provisioning of cloud resources using configuration file, and we try to use automation as much as possible to eliminate it. In addition, to increase the reliability, we set up Canary testing for new releases and configurations. Reliability is more than just building reliable systems, but we also need to run reliable systems. For that, we need to prioritize reliability. We mentioned that reliability is the most important feature, but reliability is not enough, and we need to balance velocity and reliability. Google framework for that is SRE. Implementing SRE includes both technical and cultural practices. We want to use data to guide our decisions, to foster a learning culture, and empower our teams. SRE facilitates incentive alignment across the product lifecycle by providing a common language and shared understanding, which is our aero budget. I mentioned before we need to be reliable, but it doesn't mean 100% reliability, because 100% doesn't let us take risks. So what do we do instead? We assume some level of unreliability that our users are willing to tolerate. That amount of unreliability is our budget. Aero budget creates a common incentive for business, operation, and development to balance velocity and reliability. If we have more budget, we prioritize velocity. We move faster, make changes, take risks. If we don't have enough budget, it means that we are not reliable enough. We need to stop and prioritize reliability. In SRE, we are using a customer-centric approach. Our scope to examine and measure user happiness is a user journey. Users are using your service to achieve a set of goals, and the most important one calls critical user journey. But where do we draw the line between happy user and unhappy user? We need to ask ourselves in which point our user will notice that things are down. We call that measurement a service level indicator. An SLI tells you at any moment in time how well your service is doing. Is it doing acceptably or not? Our reliability target for an SLI, called an SLO, service level objective. Aggregate that over time. It's the mathematical equivalent of aero budget. It says over this window of time, this is my target and how well am I doing against it. And we want our SLO, our target, to drive our design. In this context, I would also want to mention SLA, a term that many of you probably heard before. Service level agreement is not a part of the SRE framework, as it's mostly relevant to the business. It defines what you are willing to do, for example, money refund, if you are failing to meet your objective. To be able to achieve that, we need our SLOs, our target, to be tighter than our SLAs. By that, SLOs and aero budget align incentive across the product lifecycle and help us to make data-driven decisions. Some of the best practices around observability are that we want to encourage a culture of measurement in the organization. We want to collect that metrics that are close to the customer experience. We also want to measure how well are we doing against our targets, and our error budget burn rate. So we'll be able to react and adjust our priorities on time. We also want to measure the team's toil. And of course, we want to review our SLIs and SLOs periodically. In GCP, our tool for that is Cloud Operations Suite, and it provides several capabilities that facilitate SRE implementation, from out-of-the-box telemetry and dashboard to define SLIs, SLOs, integrated alerting on those SLOs, and incident management. I can't talk about designing for reliability and SRE without talking about non-abstract large system design. In Google, we found that addressing reliability issues during design reduces the cost later. And if we adopt an iterative style of system design and implementation, we'll be able to develop robust and scalable system at a lower cost. A journey to SRE includes both implementing SRE practices that we covered before, like SLOs, but also fostering and enabling culture, accepting failure as normal, reducing organizational silos, and making tomorrow better than today by reducing the cost of failures, using Canary deployments, and having CICD pipeline and automation in general. Finally, in this link, you can find a collection of publicly available resources for you to use, break by resource type and level, including KnowledgeD. And because I'm all about data, and feedback is an amazing gift, I would really appreciate if you take a few minutes from your time to share with me your feedback about this talk. And with that, I would like to thank you for your time, and let's move to questions.